Right, so what is shape risk? So far I've talked about interest rate risk. So in particular, we saw that the interest rate risk, is no matter if the interest rate goes up and down. If you are positioned wrongly, then you're enduring a risk, right? So and then they talk about immunization, which is about not being positioned wrongly in the market. So and when it comes to asset liability management, it's about having a portfolio of assets which got the same duration and convexity as your liabilities, right? And this could be essentially true also both for pension funds, but it could also be true in terms of if you were looking into your individual personal economy, you still want to have your asset side and liability sides, they have to match in terms of your duration. So you don't really mind if your assets and liabilities go up and down at the same time, whereas if you get hit on your asset sides and your liabilities then go up, then that's not a very desirable situation, right? So that's, in general, it's both in personal finance and in corporate finance, you want to make sure that you kind of immunize your assets to your liabilities so that they move in the same direction. That's why we talked about immunization with regards to duration and convexity, the first and second order differentials of the price function of the bond. Now comes the idea of the shape risk, which is what we are seeing here so far. I mean, if you are looking into the first order, the tangent to this price function, or if you're looking into the second order differentiation of that, which is convexity, right? In both cases, it's got something to do with parallel changes of interest rates. So we didn't talk about that. We say that even if you're looking at the whole interest rate curve, then we're saying if we see a parallel shift up or down, what is the impact of that on the price? So now the interesting question comes, does the interest rate curve, does it only change in parallel? And the answer to that is no. And here is just an example of in what ways normally we observe that the whole term structure of interest rates can change. So in this case, well, this is let's say our given term structure of interest rates, and then you can see, well, the whole thing kind of goes up by the same amount, right? So for if you take each point in this graph, it can change. It can change by a same level. That's why it's called. It's a change in the level of your yield curve, a level change, right? I can also think of this as a parallel shift. So it's a change in level, or it's also called a parallel shift. And this is, well, in many cases, this is what you would see. But also, then again, there are in so many other examples, well, you see something more like this, where you see that the slope of the yield curve changes. So that normally happens when you see that the shorter rates, they might go up or might go down, and the longer rates, they will stay the same, around the same area. And again, you will see that if you do empirical study of how the interest rates change over time, you'll see that the longer rates are a bit more stable and the shorter rates are more jumpy, which kind of makes sense. There's a lot of activity, a lot of speculation going around on the short term than on the long term. So that's why normally what you observe in the markets is the long-term rates are more stable and the short term are less stable. So already then we know that, well, it's not quite true that the interest rates always change in parallel, right? So there is also a risk associated with interest rates, which has got to do with the shape of the yield curve, and that's why it's called a shape risk. So we are not going into specifics of this, but I just want to introduce that to you in this course. So you don't have any assignments on working specifically with the shape risk. For today, there is, although one case when I want you to test and just to get an idea of how it, how you can get that into account. This is something that you will work with in your midterm project, which is more to do with doing some different scenarios of changes of interest rates and then calculate what is the impact of that on the portfolio you're looking into, right? So you get this a slope change, and then you can also get a change in curvature, right? So the curvature, it does also happen. Sometimes you have more flat yield curves, and sometimes they are less flat. So what happens is the interest rates in the middle, they change as well. And actually, there have been quite a number of studies done where people try empirically to look into different bond markets and see how the yield curves have been changing over years. And here are just some results that I got from the book of the Stavros book, where you can see some of these examples. So there were these studies done in Italy. I think these are back in the 1990s, so they are a bit old. But they show that about 94% of those changes were due to changes in the level, parallel shifts, but 5.5% were due to changes of slope. But still, you could say, well, mostly parallel. So all right, maybe that's kind of fine. So I mean, 5.5% changes of slope, but mostly still parallel shifts. And there are similar studies in Italy. But then there comes this interesting study, which is from a bit long, a while later than the other studies from Denmark. Some new data, which shows all of a sudden that there is a changes in steepness, that is the slope, which actually explain most of the changes. 86% of the changes come from that, and not from parallel shifts. So that is kind of boring a little bit, right? So far I'm telling you, you can look into duration and convexity, but duration and convexity, they assume that there are parallel shifts of interest rates. But then we see there's been a case study which shows 86% of changes of interest rates in Denmark, they are actually changes of a slope. So we don't really, it's not quite enough to look into parallel shifts and by looking into duration and convexity. And actually 11% of the cases were due to changes of curvature, right? And changes in short rates up to 10 years. So there's actually, there's hardly seen any parallel shifts for that particular study. So those studies in terms of what are the major reasons, you probably see some degree of parallel shifts kind of hidden into somewhere between 0.1 and 3 here, but in their pure form there have been changes in steepness and in short rates up to 10 years. And now the question is whether or not we can do something about that in terms of immunization. And again, in the book you can read there are also based on some work which was done around the same period. That was actually based on the Danish study showing that, well, we can't really trust the fact that we only have changes in parallel changes of interest rates. But, well, we can do more than differentiating in one dimension. You have probably done that already. You can differentiate the function with regards to several dimensions, right? You have heard of multidimensional differentiations, right? So that's essentially what this idea of factor modified duration is about, right? So, and the idea here is that you get this, this one called this the soft D. So rather than the D of P over D of F, then you have the soft D of P over soft D of F. You know that that terminology. That's essentially differentiating a function with regard to a multidimensional function. In that case, this multidimensional function is what we call F, standing for factors. Now you would say, well, why do we want to differentiate the price function now with regards to some factors, and what are these factors? Because to begin with, I told you that, well, interest rates, they're not changing parallel, but and we have 30 interest rates, and we can look into if each and every one of them are changing with some different values, right? Then we can differentiate with regards to all the 30 interest rates. But the point is, then you get a model which is kind of over-parameterized and would be overly sensitive to the errors. That's why rather than looking into all the 30 factors, because there is a high degree of interrelation between those factors anyway, so we want to find out what are the main factors. So that's why we do a factor analysis first, or a so-called principal component analysis. Has anybody done a principal component analysis? Yeah, there are some from some statistical courses. So the idea of a principal component analysis or factor analysis is to find out what are the primary sources of variations in a multidimensional series, right? So in this case, we have 30 different interest rates, and we know that the 1-year rate is very much interrelated to the 2-year rate, right? And to the 3-year rate. But if you take the 1-year rate and the 30-year rate, maybe the correlation between them is less, right? And so the idea is to in a systematic way finding out what are the linear combinations that kind of describe which are as uncorrelated as possible and describe the variability of these 30 interest rates, right? So that's what the principal component is about. So what you see here is nothing but the principal component analysis essentially is done. In this case, we want to see the changes to a given level of, the changes of any of these interest rates defined as a function of some factors, which are your principal components, multiplied by some weights for those factors, and with some error term, right? And there is a few pages in the book that you can read about how you essentially come down from that doing this principal component and come essentially from this line to that. But what is important is that this can easily, once you do your principal component analysis and you got your weights on the factors, the betas, then essentially you have this term which is called the factor modified duration, which essentially has a new element in it, which are the betas defined on the j's, which are the number. It's a set on the number of factors. So let's say if we can define the movements of the 30 interest rates with 3 factors, and the 3 factors, one of them, let's say, could represent changes in the short rate, one could be the changes in the long rate, and the third factor could be, for example, a change in the curvature. It could be, for example, a combination of the short, long, and some interest rate in the middle. So if you can take those 3 factors, if they end up being the main 3 factors or some interpretations of the 3 factors, then for each of those factors you have some factor loadings, which depend on the factor itself. For factor 1, for any of your the time points that you were looking at, it's got a factor loading, and once you get that from your principal component analysis and put it into this formula, then you get what is called a factor modified duration. You can do the same thing then with the factor modified convexity, and essentially you take the optimization model we had from before, and you can rather than using duration, in this case you are using the factor duration, and in similar fashion you can use a factor convexity and have your second order factor immunization, right? Now this is kind of a nice theoretical work, but in practice again it's shown that, well, these factors, I mean these factor loadings, these betas, are not very stable. I mean, one thing is that if you wanted to do this on the 30 interest rates, the model would be absolutely non-stable. The factor loadings you would get would be extremely error prone. But even if you do your factor immunization, which is doable, you would still get so factor loadings would change very often from almost from time to time. So every half a year, then you have to get some new ones. And what's the point of that kind of? Because the idea is that you want to have some factors which are stable over a longer period of time, right? So this is so you might get a model which seems that you're immunizing your portfolios with regards to some factor loadings today, but the factor load is not going to change in 6 months or in 1 year to a degree that your portfolio is not optimal anymore. So there is, I mean, even though the model theoretically has to perform better if this factor analysis, the principal component analysis, was essentially stable over time. If that was the case, then you would get better performance from this model. But in practice, actually, there is always still a debate whether the simpler model performs better than the more complicated model. But I wanted to introduce you the more complicated model, because the thought, I mean, some people actually have been thinking of this. Probably they went a PhD or two working with a model like this, and then the result of all that was, well, it theoretically works nice, but at the end of the day, the simpler versions maybe work better in practice, right? So then again, it comes back to sometimes simpler model, which in this case was, where we have an assumption of only parallel changes of interest rates. Actually, in practice, they do work better, and most people actually use those to some degree. They don't only use that, but you always want to, if you were working with asset liability management, you want to start with a simple model like that, and then you want to do maybe some kind of shocks to your yield curve, which are not of the only parallel shocks to your interest rates. You want to make some different kinds of shocks, and then you want to find out whether your assets and liabilities are also kind of immunized for those shocks. And that's exactly what we are going to do for your midterm assignments. That's the only thing that essentially you are not going to see in the assignments, but you're going to work with in the midterm project. All right, so that was all I had to say about this, and let's take a 15 minutes break, so 20 to 3, and then the rest of time with the assignment. I'm going to introduce the midterm assignment also, I think about 4 o'clock.